Hi everyone, welcome to my office hours. Today is June 25th, 2020, and we are going to be talking mostly about Chapter 8, Alkyl Halides and Elimination Reactions, and I'm going to do my best to get into Chapter 9 if we have time. So the main thing about Chapter 8, the main focus rather, is elimination. And elimination and substitution are sort of two sides of the same coin in that substitution uses a nucleophile and elimination uses a base. Generally, nucleophiles will be bases, so nucleophiles will be bases, but not all bases will be nucleophiles. And we can see that in due to steric hindrance that I'll go over in a little bit. So when we talk about elimination, we're talking about alpha-beta elimination. And what that means is we have our alpha carbon, and in E2, our alpha carbon is whatever is directly attached to the leaving group. So in this case, here's our alpha carbon, and then the beta carbon is whatever carbons are right next to that. So this is a beta carbon, and this as well would be a beta carbon, but it would end up with the same sort of product. In E1, on the other hand, E1, similar to SN1, is two steps, and we create a carbocation. The carbon that contains the positive charge after any rearrangements that need to occur will be our alpha carbon, and any carbons next to that will be our beta carbons. And I'll show you that in a little bit. But generally, that's the idea behind elimination. And I'm going to use the example that they had earlier with this guy right here. And generally what happens in elimination, I'm going to show you an E2 reaction. Generally what happens is we have our base. In that case, it was OH negative, but I'm just going to use B for base. Generally what happens, at least in an E2 reaction, the hydrogen, so here's our alpha carbon. Oops, let me fix that. Here's our alpha carbon, here's our beta carbon. Generally, the hydrogen on the beta carbon will be grabbed by the base at the same time as the leaving group leaves. And then this hydrogen-carbon bond moves to become the double bond between the alpha and beta carbons. And so this is the general mechanism for an E2 reaction. Okay, for E1, it's a little bit different. It has two steps, whereas E2 is one step. I just want to demonstrate how E2 and elimination work overall by having a leaving group leave and having a hydrogen being sort of stolen by a base. Okay, so so dehydrohalogenation is essentially just we're losing a hydrogen, which is the hydro part, and a halogen. So it's called dehydrohalogenation because we're losing a hydrogen and a halogen. And that's generally what we're going to see in this chapter. In chapter 9, we do see elimination using OH groups in an alcohol and then H groups. And this is known, oh, not there, sorry, an H group right here. And this would be known as dehydration because we lose an OH and an H. We lose H2O overall. And so then that's where these different names come in. So when we're talking about alkyl halides and elimination, we are talking about dehydrohalogenation. Okay? So now let's talk about alkenes just a little bit. I know today in class we went over alkenes a little bit. That's chapter 10. But I'm going to talk about it a little bit here. The stability of an alkene depends on a couple of things. So the first thing it depends on is how substituted it is, how many R groups are attached to it. And just a reminder, an R group is any carbon, carbon-carbon sort of structure, usually just an alkane group. So it could be CH2CH3, it could be CH3, it could be any number of those things. So a monosubstituted alkene has only one R group attached to the double bond, and it's less stable than disubstituted, which is less stable than tri, less stable than tetra. In addition, when we're talking about alkenes can either be cis or trans. And generally, we will talk personally, I will more likely use the E or Z designation. We talk about it a little bit more in chapter 10, so I'll leave it for that. But a general rule is that if the big groups are farther apart from each other, then the alkene is going to be more stable. So overall, trans alkenes are more stable than cis alkenes. This is not always the case, but this is a good general rule. When we have two hydrogens on either side. Okay? So now let's talk about the stability of alkenes when we make our elimination reaction. So let's say that I have my leaving group right here, and let's say that we're doing an E2 reaction. So I'm not going to specify what my base is. The only reason I'm saying we're doing an E2 reaction specifically is so I can show you everything happening in the same moment, okay? So first off, we found our alpha carbon, and then we find our beta 1 carbon, and then our beta 2 carbon. We can have up to 3 beta carbons, but in this case, there's only 2 of them, so we're just going to work with those 2. Both of these beta carbons have a hydrogen that they can lose through elimination and make a double bond between that beta carbon and the alpha carbon. So we end up with 2 products. One where beta 1 loses its hydrogen, and we end up looking like this, and one where beta 2 ends up losing its hydrogen, and we end up looking like this. If you recall from that chart that we talked about just a second ago and right here, the more substituted the alkene is, the more stable it is. So the reaction that used the hydrogen on beta 2 is going to be more stable overall. And this more stable product is called the Zeitstev product. I always spell Zeitstev wrong. I always swap the T and the S. So please forgive me if that's misspelled. But Zeitstev is the product, and then the less stable product is called the Hoffman. So you may be wondering why we would ever make the Hoffman product. But I just want you to notice here, if you look at beta 2, we can see that that carbon is more crowded. It's connected to 2 other carbons. There are bigger groups next to it, whereas beta 1 is only attached to a single carbon, which means that it's less substituted and it's easier for big bases to get into it. And so now I kind of want to talk about bases and nucleophiles and what makes a nucleophile, what makes a base. So recall back in chapter 2, I think it was, bases are anything that will grab a hydrogen. It is a hydrogen acceptor. A nucleophile, on the other hand, this is more akin to the Lewis acid Lewis base definition of a base, where it's going to donate its electrons to anything. So that could be a hydrogen, it could be a positively charged carbon, it just donates its electrons to anything. A base specifically grabs a hydrogen, okay? So let's look at something that's a strong nucleophile and a strong base, negative OH. We know negative OH is a strong base because it wants a hydrogen, but it also will regularly attack like positively charged things, like carbon plus that has 3 bonds, no lone pair, that type of thing. But on the other hand, if we have like a big bulky base such as tert butoxide, like this here, we can see here that this one here, the tert butoxide, is much bigger than this negative OH. So it's going to have a lot easier time of grabbing a very small hydrogen than fitting into a space and making a bond with this carbon plus. So this guy is not really going to work as a nucleophile, but it will work as a strong base. Now, another thing to note is if we have an elimination reaction, so let's take that other example from before. I may not draw it perfectly the same as long as we just sort of have the same idea. So if you recall, we talked about this one was beta 2, I think we did, and then this one is beta 1. Beta 1 is less sterically hindered, but it's going to make the Hoffman product, which is less stable. Beta 2 is more sterically hindered, but it's going to make the more stable Zeitstev product. And which product is going to be formed overall depends on what kind of base we use. If we use this small base that is available to go and attack the more stable beta 2, then yes, we're going to make the Zeitstev product. However, if we have a big bulky base, it's going to have a really hard time getting to beta 2, so it's going to prefer beta 1 for its elimination. And the way that I always think of it as, we can think of these things as like parking spaces. Beta 2 has like a really small parking space, but it's like way nearer to the entrance. And then beta 1 has a much bigger parking space, but it's a little far from the entrance. A tiny little bug, car, which in this case would be our OH, our small or small base rather, is going to easily fit into that small parking space. However, this guy over here, our tert butoxide, is like a big truck. It's not going to fit very well in a small parking space. So it's going to prefer this really big parking space that is sort of less ideal. So that's how I always think of it. A big base is going to want the Hoffman product because it's easier for that big base to get to that less sterically hindered carbon. Okay. So I think the next, so here it's talking about the mechanisms of elimination. Recall, SN2 is a one-step reaction, and in the same way, E2 is also a one-step reaction. And vice versa, SN1 is two steps, E1, two steps, okay? And if I were to draw the mechanism, we can see here that the leaving group leaves and the hydrogen is grabbed by the base, okay? And then we end up with this guy right here. Whereas in E1, the leaving group leaves first, we end up with a carbocation, and then the base grabs the hydrogen, and then we end up with our double bond, our alkene. So that's the main difference. And if we talk about the rate equations here, so if we remember when we talked about the rate equation for SN1, or SN1 and SN2, the rate equation for SN2 included both the substrate, which is our alkyl halide, and our nucleophile. In the same vein, our E1 reaction is going to include both our alkyl halide and our base. I'm just going to put B for base, okay? And this is because it is one step, so all the reactants are already over here. On the other hand, for E1, we can see we have two steps. We have to find the slow step. And again, the slow step is going to be this first step here, which is making the carbocation. So our rate is only the concentration of our alkyl halide. Okay? So that's the main difference between E1 and E2. Okay, so let's continue on. So here's it talking about the rate. And so now let's talk about the base that we use. So the base that we use can sort of change which reaction we're going to do, whether E1 or E2 or SO1 or SN2. So if we have E2 prefers strong bases like negative OH, that kind of stuff. E1 prefers weak bases like H2O. And this is because, again, similar to SN1 and SN2, that it wants time to make its carbocation, and when given a weak base, it does get that time. Whereas given a strong base, that strong base is going to be more likely to attack the hydrogen without giving the carbocation a chance to form. Okay? And here are some common bases you'll see. Let's just go on. And again, this is talking about the substrate and making the Hoffman and the Hoffman and the Zeitstep product. So let's talk about the substrate as far as E1 and E2 go, which means our alkyl group and our leaving group. So a tertiary alkyl halide is preferred over a secondary, which is preferred over a primary for both E1 and E2. Obviously, for E1, it makes sense because when we make the alkyl halide, we want to make the most stable alkyl halide, and a tertiary alkyl halide is more stable than a secondary, which is more stable than a primary, and so on. However, E2, it's less obvious. But if we take a second and let's look at our transition state. Remember, the transition state is the sort of midpoint between the reactants and the products. So let's take that, like this secondary one right here. So we have, oops, didn't mean to do that. We have our two carbon groups on either side. And then we have a partial bromine bond, because remember, in the transition state, we have a partial bromine bond, and we also have a partial hydrogen bond. Because again, these are the two bonds that are being broken and being made, and the bromine also has a partial negative charge, and then this carbon has a partial positive charge. You see here that the partial positive charge is going on the carbon that's attached to the leaving group. So what that means is that the more substituted that carbon is that is attached to the leaving group, the more stable the transition state will be, and the better the reaction will go. So that's why E1 and E2 prefer tertiary over secondary over primary, which is a little bit different from how SN1 prefers this pattern, but SN2 does not. Okay, so this is just showing our partial bonds and everything. So this is just more examples about how this happens. And then this is regioselectivity, which we already talked about with the Zaitsev and the Hoffman product. And then stereoselectivity. This is talking about the cis-trans stereoisomers. So you see here that the trans product is preferred over the cis product, and that again is because the trans product is more stable than the cis product, because we're keeping these big groups as far apart from each other as possible. Okay, so let's talk about E2 reactions and cyclohexanes. And this may not seem like a really important thing to talk about, but it becomes more important later. So when we want to do an elimination reaction, if we're doing E2, our reactant, so our leaving group and the hydrogen, both of those, they are preferred to be anti-periplanar, and what that means is one is sticking up and one is sticking down. If we looked at this in the Newman's projection, we would see, let me just do this, we would see it look like this. So here's our hydrogen, here's our leaving group, and this is the anti-periplanar, and this is what is preferred. For the syn-periplanar, if we did the Newman's projection here, it would be the eclipsed Newman projection, which again is not preferred because it's less stable. So one, it's easier for the leaving group to leave and the hydrogen to be grabbed by the base. And two, overall, the anti-periplanar formation is more stable. So for an E2 reaction, the anti-periplanar reaction is preferred. And we can see this in this example right here. So we see that the H in the red and the Br in the red, they're anti-periplanar because one is a line pointing up and one is a line pointing down. And we can see here that this hydrogen here is the hydrogen from this here, and instead, if this methyl instead were a hydrogen, again, this guy would be the one that was preferred to react, okay? So why is this important? This is important when we come to talk about anti-periplanar geometry and chair conformations. Yay! I know all of you really love chair conformations and you love drawing them. Yep. Okay. So when we draw a chair conformation, when we're talking about anti-periplanar, generally we're going to be talking about one where the leaving group is up or down, so leaving group, and one where the hydrogen is the exact opposite. So the leaving group is axial up, and in this case, the hydrogen is opposite down. So if I were to also have another hydrogen here, the hydrogen that is going to react and leave along with this leaving group is this hydrogen right here. And for cyclohexanes, this is the only way we can really do E2 reactions. So let's say that we have a cyclohexane. Let me draw it out real quick. And we have our leaving group right here. Let's say it's just Br. And then we have a methyl group right here. So if I were to do this without trying to look at the chair conformation, see what's going on, I would say, oh, the most stable product looks like this, so this is going to be the major product. However, if we look at the chair conformation, we'll be able to see that that is not quite the case. So if I go here and I say, okay, this is going to be my bromine here, so I'll draw that going, actually, I'll make this my bromine here. And so my bromine is a solid wedge, so I'm going to draw it going straight up. Okay? My methyl group is on a dashed wedge. I'm going to put my methyl group right here, so it's going to be going straight down. Okay? And if I draw in the remaining hydrogens on either side, we can see here that this guy, the carbon with the methyl group on it, does not have a hydrogen that is anti-periplanar to Br. So instead of having the double bond formed right here, it's going to force the double bond to form on the other side. So our major product is going to look like this. Okay, even though that seems like it's the less stable, the minor product, because we have to do an elimination anti-periplanar, that means we have to make this product other than the other one that looks more stable. Okay, so let's continue on. So now let's talk about E1 reactions. So again, E1 makes a carbocation, and just a reminder, when we make a carbocation, we're able to do a hydride or a methyl shift. And a hydride and a methyl shift occurs when a positive charge sees a tertiary or quaternary carbon right next to it, right there. So it sees that secondary or that tertiary carbon right there, and it says, wow, I would be so much more stable if I was over there. So what happens is, just recall that a positively charged carbon is a carbon with 3 bonds. So this carbon right here looks like this. And so then what happens is the carbon over here, CH3, CH3, this carbon has 4 bonds, and one of them is a hydrogen. And so what happens is that the hydrogen that is a part of that tertiary carbon complex is going to move over to this carbon right here with the positive charge. And so then we end up with the positive charge moving onto the tertiary carbon. And this is because we can see here that this carbon that had the positive charge gains a 4th bond in the form of that hydrogen. And the tertiary carbon loses that hydrogen bond, so now it has 3 bonds, and now it's going to be positively charged. And this is called a 1,2 hydride shift. And obviously we call it a hydride shift because we're moving a hydrogen. We call it a 1,2 shift because these types of shifts are only going to occur between carbons that are adjacent to one another. So we see here this one is adjacent to this one. If we had something like this, and we had our positive charge over here, this positive charge is 2 carbons away from that tertiary carbon, so it's not going to be able to do a shift. Okay. Another type of shift is called a 1,2 methyl shift, and this occurs when there are no hydrogens for that carbon to shift. So like, let's say instead of a hydrogen right here, that was just a methyl group. Okay. Then we would have let me get my eraser, we would have a methyl group right here, and instead of moving that hydrogen, we move a methyl group. And so then this is called a 1,2 methyl shift, okay? Because we're moving a methyl group instead of a hydrogen group now, okay? Let's just continue on. I know there's an example in a second. So right here, so here's an example of the E1 mechanism. So obviously, one thing to note is that this reaction contains heat. So E1 and SN1, they both create a carbocation. It's like they both create this guy. And they both use a weak base and a weak nucleophile, like, I don't know, H2O. So SN2, or sorry, not SN2, but SN1 and E1 will always occur simultaneously. The way that we force one to occur over the other is to use different environmental situations, such as using heat to encourage the elimination reaction to occur. Okay? So when we see heat, we know that it's probably going to end up being an elimination reaction. So let's go ahead and start drawing these lines. So we see a weak nucleophile, weak base, and we see heat. So we're going to say, oh, this is probably going to be E1. So and I'm working on making you guys a chart comparing E1, E2, SN1, and SN2. Just be on the lookout for that when I do my review on Saturday. So the first step for E1 is the leaving group leaves, and we end up with a carbocation. Okay? And I'll give you guys a second to try and think of what you're supposed to do next. But pause the video if you're watching it, or just take a few seconds if you're live, and then we'll just continue on. All right, and so we can see here that this carbon here, this is a secondary carbocation. It's right next to a quaternary carbon. So that positive charge sees that quaternary carbon, and it's like, oh, look there, it's much more stable. I want to be like that. So what occurs is a 1,2 methyl shift where one of these methyl groups moves over to that secondary carbon, and we end up with this guy right here. Our positive charge is moved here, and now we have a tertiary carbocation. Okay? And then what happens is that is why it's important to not mark our alpha carbon until we're sure we have our final carbocation, at least for E1, because here's our alpha carbon, and then here are our 2 beta carbons. If we went up here at our reagent and we said, oh, here's our alpha carbon, here are our 2 beta carbons, then we would get the wrong answer, okay? So now let me go ahead and draw one of the hydrogens on one of these beta carbons. And additionally, both of these beta carbons will yield the exact same product. So we only really need to write one of them. So now we have H2O, so HOH. It's going to grab that hydrogen, and then that hydrogen bond is going to move and become a double bond right there. And then we end up with our final product, okay? So that is an E1 reaction. Just make sure to be on the lookout for those carbocation rearrangements. Okay. So when we're talking, so competition between E1 and E2, generally E2 is going to react with a primary alkyl halide. E1 can react with either secondary or tertiary, and E1 is going to prefer a weaker base, a weaker nucleophile. Okay, and then again, this is just reiterating what I said before. It's that SN1 and E1 both form a carbocation intermediate, and thus they will both occur using that weak nucleophile, weak base. And so we're always going to have SN1 and E1 occurring simultaneously. So if we're doing something like a synthesis like in the lab or something, using E1 or SN1 is probably less ideal than using a different type of reaction like SN2 or E2. Okay? So here we can see that if we use a tertiary alkyl halide with a strong base, we're going to make the E2 product. And again, this is because E2 likes to happen in one step. And so if we have a strong base, then it's going to react faster, and thus E2 will form. And we're not going to do an SN2 reaction, again, because it's too sterically hindered to do SN2, but it's not too sterically hindered to lose a hydrogen. On the other hand, if we have a weak nucleophile and a weak base, then that gives the reaction time to form a carbocation and thus do SN1 and E1. Okay? So let's go ahead and make like a really dirty chart here. So let's say that we have a primary alkyl halide, or actually, let's say that we have a methyl alkyl halide, a primary alkyl halide, a secondary alkyl halide, and a tertiary alkyl halide. We know that methyl alkyl halides will only ever do SN2 reactions, okay? On the other hand, primary alkyl halides will both do SN2 and E2. Secondary, it will do all of the above, SN2, E2. And again, I'm putting SN1 and E1 together because they will react, they will both occur at the same time. And then for tertiary, we're either going to have E2 or SN1 and E1. Okay? And so now what we have to do is we have to compare what we're using as our base or our nucleophile. E2 likes a strong and bulky base. Because again, if it's bulky, it's not going to want to go through SN2. And SN1 and E1, they like a weak nucleophile, weak base. SN2 likes a strong and small nucleophile. Okay, I'm gonna make a little bit of a better chart later. This is just a hard and fast chart. What I usually do when I'm trying to figure out these equations or these questions, like it's giving me a reaction, it's saying, is this E1, E2, SN1, SN2? I would say, okay, first let's look at our alkyl halide. If it's a methyl alkyl halide, then bam, we're done. It's SN2. If it's a primary, it's either going to be SN2 or E2. Secondary, we have all of our options. Tertiary, either E2 or SN1 and E1. Okay? So We will get into that. I'm going to make a chart later that I'll give to you guys, but this is just like a quick thing just to compare all of them. Hold on one second. Okay. So again, this is just going along talking about predicting reaction mechanisms of SN1, SN2, E1, or E2. We can see we have a strong base and a nucleophile. Oh, that'll be SN2 and E2. A strong bulky base, going to be preferred to be E2. And then a weak nucleophile, weak base, SN1 and E1. Okay, and then here's a chart here. This is a good chart if you want to memorize it, but I find that there are some easier ways to organize this chart. So again, I'll come back to that later. Okay, so let's talk about E2 in alkyne synthesis. So you know that alkane, A-N-E, is a carbon hydrogen, a carbohydrate with only carbon-carbon single bonds. An alkene, E-N-E, has a carbon-carbon double bond, and an alkyne, Y-N-E, has a carbon-carbon triple bond. Okay? And so when we're talking about E2, we see that, we form an alkene with our first E2 reaction. If we were able to do that again, we can make an alkyne. And that's what's happening here with these different dihalides. And essentially what these dihalides are, it's something with two halogens, dihalide. And they can either be vicinal or geminal. I always remember geminal being like, oh, it's like a Gemini. They're twins. They're on the same carbon. In a vicinal dihalide, they're in the same vicinity. So when we're talking about E2 reactions with dihalides, essentially we're going to be doing an E2 reaction twice. We lose a hydrogen, we lose a leaving group once, and then we do it again. We lose a hydrogen, we lose a leaving group. So essentially it's just E2 twice. Okay? So that is the end of chapter 8. I'm going to pause the recording, see if anybody has any questions, and then we will continue on to chapter 9. I can't guarantee that I will be able to finish that today, but we should get quite a bit done. Okay, so now we're going to get into chapter 9, alcohols, ethers, epoxides, thiols, and sulfides. Honestly, what my opinion about this chapter is I sort of like to uh, cut it down the middle just like this. And I take on alcohols, ethers, and epoxides on their own, and then thiols and sulfides on their own as well. Because each one of these, they're similar, but they're different. The whole reason that they're grouped together is that O and S have very similar chemical properties. So they're going to go through roughly the same types of reactions. And that's the general reason why they are grouped together. But I like to tackle them one group at a time, with alcohols, ethers, and epoxides being one group, and then thiols and sulfides being another group. The book organizes this a little bit differently, so I might end up jumping around this PowerPoint a little bit, but just bear with me. So alcohols, ethers, and epoxides. So obviously an alcohol is like any R group, so anything like this with an OH on the end. An ether, you have two R groups on either side, so it's technically I like to think of it as similar to an alcohol, except of an H, we just have another R group. And then an epoxide is a cyclic ring made up of one oxygen and two carbons linked all together. Okay, and so I think the first section of this chapter talks about naming alcohols, or talking about naming alcohols. So when we're sort of giving an alcohol a primary, secondary, or tertiary sort of name, we think of it in the same way that we think of hydrogens being primary, secondary, or tertiary. It depends on what kind of carbon they are attached to. So this alcohol is attached to a secondary carbon, so it's a secondary alcohol. This alcohol here is attached to a primary carbon, so it's going to be a primary alcohol. This OH is attached to a tertiary carbon, so it's going to be a tertiary alcohol, and so on. And so now let's talk a little bit about naming. So obviously the first thing you're going to do is you're going to find the parent chain. And the parent chain for an alcohol is the longest continuous carbon chain that includes the OH bond. So in this case, this would be our parent chain. Okay? And so if I look at this parent chain, I say there's 1, 2, 3, 4, 5, 6 carbons. Hopefully I counted that correctly. And so then we would say this is going to be a hex. It's going to be, let me choose a different color so you can actually see it. It's going to be the base name of the parent name is going to be hexane. Okay? But then we see, oh, there's an OH group right here. So it's going to be hexane all. And so we also have to tell our readers, tell whoever we're trying to communicate this to, which carbon our OH is on. So now we have to number our carbon chain. And again, as always, there are two ways to number this chain, either left to right, like this, 1, 2, 3, 4, 5, 6, or right to left, 1, 2, 3, 4, 5, 6. And so we can see here that we can either put the OH on the 3 or on the 4. We are going to always want to give the OH group priority over any alkyl groups, which is any group that's only made up of carbons and hydrogens. Okay, so in this case, we are going to put oxygen on 3 and prefer that top way of numbering. So this is going to be hexane 3 all, because that tells us our all group or our hydroxy group is on carbon 3, and then all we're going to do is add the 4-methyl in front of it. So it's 4-methyl hexane 3 all. Okay? All right. So let's continue on. So here are some more examples. When we're talking about cycloalcohols, so in this case it would be cyclohexanol, we do not always have to put like the cyclohexane 1 all. Sometimes we can just say cyclohexanol. But I prefer doing it this way. The whole reason why we don't have to put that 1 there is because it's sort of assumed that if we don't put the 1 there, it's going to be on our 1 carbon. Because we can honestly number a cyclo anyway, and it would still be valid. But we always have to put the 1 when we're talking about an OH group on the first carbon of a carbon chain, because we cannot assume that any one of these carbons can be 1. Okay? So I like to put the 1 here, even though it's not technically needed. I like putting it there just for the sake of clarity, so I don't confuse myself and I don't confuse other people. So this would be cyclohexane 1 all. And then this one, again, we have to number it giving the alcohol the lowest number possible because it takes priority over those alkane groups. So the OH is 1, 2, 3, 4, 5, 6. And we could number the other way, but again, we want to give substituents the lowest number possible. So we're going to put these methyls on 3 instead of going the other way around. So just naming this like before, it would be 3, 3, dimethyl this is the long name, hexane 1 all. Okay, but I'm not quite done because you see here the carbon 1 has stereochemistry. So I'll give you I'll just do a quick refresher on stereochemistry. We're going to assign priority. OH is 1, this group is going to be 2, this group is going to be 3, and then this H right here is going to be our lowest priority. So now we see that our lowest priority is not in the front. So what I'm going to do is I'm going to redraw this like this. So all I'm doing is I'm sort of flipping this guy around so that 3 is on the top. The priority 3 is on the top. Priority 2 is off to the side. I'm going to sneeze. 1 priority is here, and then 4 priorities right here. Thank you if you just blessed me. But so essentially what we're going to do, just a reminder, we're going to pick this guy up by 3, and then we're going to twirl him around so that 4 is on our dashed wedge. So 4 is going to go where 1 is going to go where 2 is, etc. So 4 goes here, 1 goes here, and then 2 goes here. And then we see that our stereochemistry is going to be R. So that was just like a quick refresher on how you do RS configurations when the lowest priority group is in the front or not in the back. So this would be an R 3,3 dimethylcyclohexane 1 all. Okay? Perfect. Okay, let's just continue on. And so there are certain common names that you might hear throughout your career. I know most people call 2-propanol isopropyl alcohol. I'm sure that a lot of people has heard. I can't remember. Is isopropyl alcohol the one that we use on like nail polish? I don't know. I don't paint my nails that often, but I'm not sure. But you'll hear isopropyl alcohol a lot more than 2-propanol. Now, what do we do if we have multiple alcohol groups? OH groups, hydroxy groups. Well, before we said, oh, if we have 2 methyl groups, for example, like we had this guy and we had 2 methyl groups on it, we would just call those dimethyl. And then we'd number it. So this would be like 1, 2, 3, 4 dimethyl hexane. And so we're going to do exactly the same thing here, except we're going to move the numbers over. So it's like 1, 2, 3, 1, 2, instead of, so this one would be 4, 4 dimethyl hexane. But if instead these methyl groups were OH groups, then this would be, oh, I'm sorry, that shouldn't be 4, 4, that should be 3, 4, sorry. It would be hexane 3, 4, there shouldn't be dash, 3, 4, diol. And that di in front of all just means we have 2. A tri in front of ol means it's going to be 3, and so on. It's the same rules as before, except now we're looking at the suffix instead of the prefix. Okay. Okay, so now when we're naming ethers, it's going to be a little bit different. There are technically 2 ways to name these. I prefer the second way. So essentially what you do in the second way, which I'm going to teach you right now, is you find the parent chain, aka whichever chain is longer that is connected to that O group. So like here's 1, 2, 3, 4, 5 versus 1, 2. So obviously the pentane group is going to be our parent chain. And then the lower group, we take the base name, so eth, so like ethyl, eth for 2 carbons, and we add oxy to tell us that there's an oxygen at the end. So this is ethoxypentane. So let's make up a quick example here, right here. So now I have to find out which one's the parent chain. I go, okay, so this one's 1, 2, 3, 4, 5, and this one has 1, 2, 3. This is going to be pentane versus propane. Obviously, pentane is a longer chain than propane, so our parent name is going to be pentane. So now what we do is we get rid of that A and E, and we change it into propoxy because we have an oxygen attached to that propyl group. So it's going to be propoxy pentane. Okay? The other way you can name these is you name either side of the chain here. So like in this example, this one right here, it would be pentyl ethyl ether. Like we see here, ethyl methyl ether, and so on. Okay? So properties of alcohols, again, alcohols, obviously they have hydrogen bonding because an OH group has a hydrogen bond. And then we can see here that the increasing ability of hydrogen bonding, it decreases with more steric hindrance, which makes sense because there's less room for that, if there's less room for hydrogen bonding to occur if there's a lot of steric hindrance. Okay, and this was all covered in chapter 3, I think. So if you need to go back, just review that. And then physical properties, again, same thing as with chapter 3. And so now let's talk about crown ethers. So crown ethers look really scary, but they're not. The main thing about crown ethers is you should know how to name them, and you should know like what is important about them. So we can see here that to name a crown, it's in the general format of X, crown, Y. The X is going to be how many atoms there are total in the crown. Y is how many oxygen atoms you have. So in this case, in this first one, we see a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's the 12 part of the crown. And then we have 1, 2, 3, 4 oxygens. That's the 4 part. And so then you just do that with all these other ones. It's way easier than it looks. So now the importance of these crown ethers is that these oxygens are obviously going to be more electronegative than the carbons around them. So these oxygens are always going to be are going to be partially negative. And so that partial negative charge is all sort of combined into this middle section right here. So it does a really good job of separating out salts. It's like Li plus. Okay? So, and then different types of crown ethers will separate different types of or different types of cations, where the bigger the crown, the bigger the cation, and you can see this in the periodic table. I don't have it memorized, but I think one example that they do have an example up here where, yeah, we can see here that the K, the potassium ion, is much bigger than the lithium ion, so it takes a larger crown to sort of trap it, okay? And so then we can use these sort of in order to make nucleophiles stronger and to make a better SN2 reaction. This is sort of a little advanced, but I recommend reading about it and learning about it. All right. And I think that's about all the time that I have today for my office hours. Again, let me know if you have any additional questions and I will answer them as soon as possible.